In this video, we'll look at piecewise functions. Now, a piecewise function is just a function that's created by multiple equations for different parts of the domain. And typically you'll see it where you get f of x equals, you have a brace, and then you have multiple equations, and for each of those equations, it's going to have a specific aspect of the domain in which you use that specific equation. So for this one, when I see f of x equals 1/3 x plus 2, I'm going to use that only when my x value is greater than 3. In contrast, I will use the f of x equals 2x minus 1 whenever it's less than or equal to 3. And if I graphed it, you would see there's a solid dot for the 2x minus 1 at 3, and there's that graph. And here, this is the x 1/3 x plus 2, and it's a hollow dot there at 3 because it cannot be 3. So you could be expected to do many of the same things you do with trying to determine things with functions. For example, evaluating the function at a specific x value, finding a specific x for a given value of f of x, find the domain, the range, the intercepts, and also this one new aspect of determining whether the graph is continuous. And to be continuous, it has to have no gaps or holes in it. So you can think about if I'm taking a pencil and I go from one side of my graph to the other, am I able to follow it and never have to pick up my pencil to get to another part of the graph? And also, as I'm taking my pencil, do I never go through any holes in my graph? So say here is my function, and it's already graphed for me, and I'm going to use the graph to determine some different aspects. And you can tell it's piecewise because we have the two different aspects that are quite different. So I go through the domain. Just like I'd go through the domain of any function, I'm looking at my x values. And when I do that, I see that my x values go no further to the right than 11, and when they go to the left towards the negatives, while my graph goes off here at -3, the arrow tells me it's going on forever. There's no actual stop to it, which means that all negative x's will be included in my domain. So I'm going from -infinity up to 11. So that means I could say that x is less than or equal to 11, or I could say that I'm looking at an interval notation from -infinity up to 11 with the bracket because that is a solid dot there, a solid point. When I look at my range, I'm looking how high and how low does my values go. They go all the way up to the 1/6, so a y value of 6, and they continue to go down infinitely, and the arrow tells me it's going to keep going on into the -infinity. So my y's are less than or equal to 6. Or I could use interval notation, say -infinity to 6, and a bracket on the 6. If I wanted to evaluate this function at 1, I'd be looking at where is x equal 1, and I have to pay attention. I have a hollow dot at 1,1 and a solid dot at 1,6. So I'd go with the solid point whenever I'm choosing between those two. So f of 1 would equal 6. Now if I ask for the x-intercepts, I'm looking at where all does my graph hit the x-axis. And in this case, it hits at 3 different places: -2, 0, 3, 0, and 9, 0. And lastly, is this graph continuous? Well, if I think about it, if I take my pencil and I'm drawing along my graph, and I keep going, I gotta ask myself, well, how do I get down to the other part? Well, I have to pick up my pencil, and then I come down, and then I continue my graph. Additionally, there's a hole right there. So I had to pick up, I have a hole in my graph, so this cannot be a continuous function. Alright, so let's look at another example starting algebraically. Say I have x squared minus 4 when x is less than 0, and 2/5 x minus 4 when x is greater than or equal to 0. So if I'm looking at my domain, there's no limiting factors. I don't have any of my problems that have an x in the denominator, and I have no radicals with an even index. So my domain in this case includes all real numbers. When I look at my range, I want to graph it to see what this graph would look like. And this is the graph of this piecewise function. Now while the x squared minus 4 would have a hollow dot at 0, -4, the 2/5 x minus 4 would have a solid dot at 0, -4. So what I know is that when I look at my y values, I go as low as -4 and I go up through infinity. So I could write that y is greater than or equal to -4, or I could write it as -4 to infinity using the interval notation. If I wanted to evaluate this function at f of -3, well, I'd say -3 is less than 0, so I would want to use my first equation. So I would be doing f of -3, and I'd be using the x squared minus 4. So -3 squared minus 4, 9 minus 4, this would be 5. So at -3, 5, it would show up right here. So I know I've done my point correctly. I've done my equations correct. Say I want to do f of 5. So 5 is greater than 0, so I would be using the second equation. So f of x of 2/5 x minus 4. I plug in a 5, I simplify and get 2 minus 4, so f of 5 is -2. And 5, -2 right here, again, point shows up correctly on my graph. Now maybe I want to know, is this graph continuous? So if I start up here and I follow it downward, I see so far I've got no holes, and right here where it transitions to the other part of my function, I have a solid dot. That point does exist, there's no gap there, and my pencil would still be on the paper, and I could now start to follow the straight line 2/5 x minus 4. So yes, this would be a continuous function.